Okay, we're going to see if we can do this in about 6 minutes here. What we're going to do is we're going to try and find the magnetic field for any R less than big R. Big R is the radius of our wire. So we have a current carrying wire here. It's for your imagination, it's probably bigger than just a little hair-sized wire. So a big copper wire, imagine that. And then we're also going to find B for R greater than or equal to big R. Well, this is an application of Ampere's law, but we're going to add a little complicating factor. We're not going to have a uniform current density. We're going to say that the current density is a function of R. So B is just some constant. We don't know what it is. It's just symbolized with B. And what that does is it complicates figuring out what is the current that's enclosed in our Amperian loop. So when we're dealing with little r less than big R, and if this is our Amperian loop right here, and what we want to do is we want to find the magnetic field at some distance r away from the center. So we want to find the magnetic field right there. That's what is indicated by this B. And we have a closed loop right here. So it's a line integral. It's closed. That's what that symbol means. And the complicating factor is what is the current that's enclosed by our Amperian loop. So to do that, we are going to remind ourselves that if we have just a little bit of area that is described not by this entire circle, but by the thickness of this little piece of current carrying wire. So what we have is a thickness dr, so in between my two little arrows there is some thickness dr, and then once all the way around is the length. So in a way, you can kind of think of it, if you took this and you unwrapped it, and we fold that thing, unfold that thing, and so we've got a line, and that thing's going to be of length 2 pi r, and thickness right here is dr, and so that's going to give us our area. So we've got the current density, J. Well, here we might as well go ahead and describe J in terms given up here. That's BR. And then the area of this is just going to be 2 pi r dr. And we're going to add that up all the way around. Well, that's not true. We're going to add that up from 0 out to whatever our R is, and that's going to give us our current, and that's a pretty simple integral. So this describes the current enclosed by some Amperian loop of some radius r, and that is what we will use to describe the current on Ampere's law here. So let's rewrite I this way. So I is a function of little r. And what we're doing is, remember, we're finding out what is the magnetic field at some distance r from the center. So we're finding out that magnetic field. And our Amperian loop, that Amperian loop is described as adding up all of the little drs. So we've got a dr there, dr there, dr there, dr there, dr there. And if you add those up, of course, that's just the circumference of our little mental construct known as an Amperian loop. And by the way, we can get rid of the dot product because all of the little drs are always going to be parallel to the magnetic field direction. And that magnetic field is going to be constant at any given r. This is going to be constant. The strength of it is going to be constant all the way around. Well, now we end up with a very simple relationship, and we can solve this for B. And this describes the strength of our magnetic field as a function of R. You could also state an important relationship this way. The magnetic field strength is proportional to the square of the distance. Well, what about, by the way, this was for R less than big R. How about whenever R is greater than or equal to R? So here we remind ourselves that any Amperian loop bigger than capital R is going to enclose the entire current carrying wire. And so that means our little r would actually be big R. And so let's keep that in mind whenever we use Ampere's law here. And we would simply say mu naught, and for I, it would be 2 pi b r cubed over 3. And that is going to be, again, e times 2 pi r. That side doesn't change. And we can simplify. We end up with the magnetic field strength is mu naught times little b, which is a constant, times r cubed, capital R cubed, which is also a constant, over 3r. Yep. And so this describes the magnetic field strength anytime little r is bigger than capital R. And let's just note this important relationship here. Constant, 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 and so we can state that the magnetic field is proportional to 1 over R.